Okay. So good afternoon, everybody. We are ready to start for the afternoon section of this paper presentation. The first talk is from Fergus Imrie from Oxford. He will talk to us about deep generative models for 3D compound design. Fergus.
Thanks. First of all, I'd just like to say a big thank you to the organizers for arranging 3DSIG this year and for giving me the opportunity to speak. So today, I'm going to be talking about some ongoing work on deep generative models for 3D compound design. So if you're familiar with any of the literature on this, you'll have seen there's been a massive explosion in publications trying to use deep generative models in order to suggest new compounds in the literature. And these are just three recent examples of some of maybe the more high-profile cases. Fundamentally, what a lot of these methods are trying to do, and the way they go about it, is to use language models, so things like recurrent neural networks, in order to learn how to produce smile strings representations of molecules. Although there have been several more recent efforts that have used more a graph-based representation of molecules. So the two generative tasks that have typically been addressed by the publications to date are either what I'm calling arbitrary molecule generation on the left-hand side, which is where the goal is to learn to reproduce some kind of prior or training distribution of molecules, whether that's a very general set, such as arbitrary molecules from, say, zinc or Kemble, or whether that's a much more focused set, say you're trying to produce inhibitors for a particular protein target. And on the right-hand side, more recently, people have been focused more on molecular optimization. And this is where you take a starting point, such as the compounds on the left-hand side of that figure, and you try and optimize one or several of its chemical properties, normally typically subject to some form of similarity constraints. You don't want your optimized molecule to look too different from your starting point. And the methods to date that have been published that address these two tasks have shown a lot of promise and is a very active area for research. But there are several issues with these methods. And they really rely around the scope of tasks that these can do. So the user typically has very little control in the design process with the methods to date. It's very hard normally to impose any constraint on the type or nature of the compound you want generated. And finally, the methods that have been developed so far are really only applicable to these tasks and can be very challenging to accept to any other type of design tasks that have been that you might want to address during, say, a drug discovery project. So today we're going to look at two really different tasks from those that have been proposed so far, and these are scaffold hopping and fragment linking, which are two tasks within the lead optimization and fragment-based drug discovery processes, respectively, that these existing methods are kind of inherently can't handle due to the nature of the inputs and kind of outputs we want to produce. So in both cases here, we're wanting to take kind of two fragments or two substructures of the molecule and retain those parts of the molecule, but join them up with some form of linker compound or a new core, say, of the molecule. And crucially, and something we'll refer back to later here, is that one of the desired properties of your new generated molecule is that in 3D space, the compound you have generated should be able to retain a very similar conformation to either the fragments or the original molecule that you're trying to scaffold hop from. And you can see in this example, these are all structures taken from the PDB. The fragments that you've joined occupy very similar spaces in the protein binding site, and that's ideally what you want your generated compounds to look like. So again, if we just formulate this problem slightly more specifically, what we're trying to do is we're trying to take these two fragments and we're trying to design something that links them together in the context of the protein pocket. And so how might you go about this? So computationally, I've kind of already said that the existing deep learning type models are unable to do this. But what other methods can? These aren't new problems. There are methods that exist. So we looked quite extensively at the literature, and we found that all of the previous methods for this task were database-driven. So they have a database of linkers that you might like or are chosen in some way, and then they score, rank, filter those by some set of criteria in order to select from that linker set the best linker or the right molecule in order to make from those starting fragments. And so there's a couple of kind of inherent constraints here, right? If you're only filtering a predefined set of linkers, you can't suggest anything that's not in that set, and you can't explore any chemical space beyond that set. So if something in that linker database doesn't fit the task, doesn't fit the specific example you're trying to kind of solve, you're going to be unable to do so. So we've tried to approach this in a really fundamentally different way, and have proposed a deep learning method that we've called delinker that takes two fragments together, as well as some basic structural information, such as, say, the distance and angle between the fragments you're looking to join together, and proposes new compounds incorporating those two fragments. We still use a database of linkers in order to teach our model how it's going to join these two compounds, but ultimately, we really want our method to be able to use the specific context and the structural constraints of the fragments that we're actually wanting to join in any given case. So for the remainder of this talk, I'm going to speak briefly on a kind of a high level about how we go about generating new molecules, then touch on how we actually trained our system in order to do this, and then for the remainder of the talk, really focus on how we validated that this approach works. So firstly, how do we generate molecules? So we use graph-based neural networks, and we start by converting the fragments that we want to link into a graph. So in this picture, your colored nodes represent atoms of different atom types, and the edges between those nodes in the graph just represent the edges. So we take those starting fragments, and we give our model a set of additional nodes to use as a building block with which to design the linker that's going to join those two fragments together. Our model then goes through an iterative process of building up the new molecule bond by bond. So at each point, we first consider from a fixed node all possible other atoms that we might want to join this node to, together with doing nothing. Once we've selected which two nodes or atoms in our graph should be joined up, we then decide what we're going to label that edge with. So is it going to be a single bond, a double bond, or a triple bond? And then finally, we perform an update step on our graph in order to allow our model to understand how it's changed the graph and what our new molecule looks like. We then iterate that process of edge selection, labeling, and this update step until this process terminates, when hopefully we've got a joined up molecule that is now our generated full molecule that our system proposes. And you note here that it may or may not use all of the building blocks we gave it at the start. So in this example, it's used most of them, but it's chosen not to use two of them. So this is how we generate molecules. I guess, how do we train our system to do so? Technically speaking, we train our system in a supervised manner under a variational autoencoder framework. So really what that means is we take these pairs of unlinked fragments with the structural constraints, and have this linked fragment, and this is the pair. This is the input pair, and we train our model to reproduce these linked fragments. So we first convert them into a graph, and then we run a graph neural network. In this case, we take a message passing neural network in order to encode each of these nodes. So you'll see each of the nodes in our graph has this little feature vector associated with it that's initially fixed based on the atom type associated with the node, that then our machine learning model updates according to the connectivity of the graph in a learnt manner. So we don't tell it how to update this, it chooses how to. If we were to naively combine these two sets of encodings, given that we're training to reproduce the linked fragments, what would happen is our system would generate into a basic autoencoder, and it would just ignore all of this top line. And we obviously don't want our method to do that, because when we actually come to generate things, we won't know what the linked fragments are. So in order to combine these two encodings together, in order to generate a molecule from it, we go through this process of compressing down this representation to as minimal a form as possible before combining it with the representation for the unlinked fragments. And then we decode this representation according to the generation process I've just previously described. Now, when we come to actually generate, as I mentioned, we don't have access to the linked fragments, and so this is where the variational autoencoder portion of our model comes in. And we're able to sample these vectors down here from random noise and combine them with the encoding that's learnt of the fragments, and we hope to generate a diverse array of samples, but that hopefully all fit the structural constraints of the problem that we're trying to address here. So we know how our method is going to generate molecules, we know how we're going to train it, but next, kind of how are we going to validate this system? What are we going to train it on, and what are we going to test on? So there's obviously not an abundance of pairs of unlinked fragments and linked fragments, which is what I've said we're going to use to train our system. So we create a somewhat synthetic set. We take a 250,000 molecule subset of zinc, which is, I guess, a synthetically purchasable set of molecules, and generate conformers of these molecules using RDKit that we're going to use as the base conformer, just the base structural information that we're going to extract whatever structural features we need. We then snip these molecules up using standard Brix rules from the matched molecular pair field of research. So effectively, we cut at all acyclic single bonds to produce fragmentations of the original molecule that we can use for this paired training process. Now, obviously, there's not just one way of snipping up this molecule in the manner I've defined, and so we can get multiple examples for the same starting molecule. And we do this for all of the molecules in the zinc set, and this defines our training set. Now, obviously, that's using generated conformers, which are not necessarily realistic of real-world, I guess, protein binding sites. So in order to test our model, we take the CASF 2016 set, which is a subset of the PDB bind set that is based on a diverse range of protein ligand complexes, all with experimentally verified crystal active conformations. And we fragment that in the same way as before, and this is just one example of that. And then we also take several examples from the fragment linking and scaffold topping literature, where we have both the crystal structure of the starting point and of the actual endpoint. So we're not biasing towards this snipping up process, so we can check our method would actually work in a more realistic example of what a prospective test might look like. So we have a look at these two test sets, and so what we do is for every set of starting pairs of fragments, we generate 250 possible linked molecules using our deep learning system, and our main comparison is going to be to a database-based system, where what we've done is we've taken all of the linkers in our training set for this system, and we've called that our database of possible linkers, and we've sampled from that set as a comparison. So the first thing we wanted to do was look at whether or not the molecules that we've proposed are sensible, first in a 2D setting. And so these are the metrics we've looked to assess by. The first is a validity metric, which is just, did we actually join together the two fragments, or was our system unsuccessful in doing so? And there might be good or bad reasons for that, depending on the context. The next, we want to look at how many of our molecules are actually unique. We obviously don't want a lot of redundancy of the generated molecules. We next want to look at novelty. So we want to say, is the linker that was used to join these two molecules together, was that in our training set or not? And we can discuss, what we might want from that. We also look at recovered, so did it remake the starting point? A lot of these are based on snipped up examples, so you have at least one ground truth. And finally, we look based on some simple 2D property filters, such as synthetic accessibility scores and the like, as to are these molecules even sensible if from, say, a medchem point of view or a synthetic chemistry point of view. And so what we see when we compare on both a subset of our training set that we've held out for some validation and this test set that I've described is that our method, delinker, generates a high proportion of novel molecules while a lot of them pass 2D chemical filters. And actually, we recover more of the original molecules than the database solution does. So after this, we kind of feel like, okay, right, our system's generating sensible things. But as I mentioned at the start, we want these things to look correct in 3D space. So the next test we do is we check to see, are these metrics in a 3D setting sensible? So I've got 3 examples of conformers of 2 molecules, where on the left it's obviously a very good match, and we have 3 different metrics for determining this based on different things. And I've got another example on the right-hand side, where it's the same 2 molecules, but maybe a different conformer of the first one, where you can see it's obviously quite a poor match. And so this is effectively how we assessed our system in a 3D sense, is for all of the generated conformers. Sorry, for all of the generated molecules, we produced a lot of conformers and scored all of those with these 2 metrics. And we find that our deep learning method generated a substantially higher proportion of molecules that looked similar in a 3D setting versus the database solution by all of the metrics we looked to assess at all of the similarity cutoffs that we looked at. So just quickly, obviously, they're all on relatively synthetic examples where we've either snipped up molecules or used generated conformers. So we've first got this first case study, which was on a protein target linked to tuberculosis, where on the left-hand side, they ran a fragment screen, and they found that this fragment bound in 2 copies in the same protein site. In their paper, they explored linking strategies where they developed 3 potent hits for this target. We ran the left-hand side, the starting fragments through our delinker tool, and we actually recovered all 3 of the hits they identified, as well as many more that when we assessed them through docking, had similar or even sometimes better docking scores than the actual hits that were identified. Finally, I'd like to leave you with an example where no matter how much you like your database, you would have been unable to solve your problem, even if you'd searched your database exhaustively. So we took this example on the left-hand side that was in the CASF set, where you can see the linker between the 2 is, I think it's a 7-carbon chain, and a fairly sizable gap between the 2 molecules. So we used our system to generate just 250 possible solutions, and we found these 5 molecules, as well as the original linker, that all had very high similarity to the shape of the original molecule and their fragments. We then did an exhaustive search of our database that contains over 10,000 different linkers, and we found no good matches within our entire database, and these were just the best ones that just, when you look at the 3D conformer, they just don't fit. So however much you like your database, there are some examples where it won't work, and this, we feel, is the power of these de novo design-based methods. So with that, I'd like to say thank you to my supervisors, Professor Charlotte Dean, Professor Mahela van der Schaar, and Dr. Anthony Bradley. Invite any questions, but also say, come and see me at my poster tonight at A064. Thank you. Ooh, there's someone.
Just a single question. So in the training set you created, the conformations of the sidechain correspond to the original conformation with the linker, right? But you could expect that in reality the chi-angles of the sidechain would change, right? They would not necessarily be aligned. Have you tried like perturbing the chi-angles before passing it to the training set?
You make a really good point, and that is one of the limitations of the training set. I guess we feel from a validation perspective that we've showed that even with that limitation, when we've tested this on real-life examples where we've got the starting point and the end, kind of the end PDB structures, where they actually have shifted in the way you've described, our method is still able to adapt to those situations. So we did look at what happens if we do perturb the conformers a little bit, and we found that our method doesn't generate the exact same molecules, but they're actually relatively similar. So the similarity of what we would generate under those two circumstances is quite high. We haven't looked at incorporating that into the training process there, and that might be something interesting to explore.
Okay.
Thank you.
Thanks for the great work.
Thank you very much for the great talk. So one clarification I'm curious about is, I see that the linker in the molecular space is connecting subgraphs together. So what is the operation in the latent space?
So I suppose we don't try, so there's, I guess, several methods in the literature that have been proposed, I guess, to navigate this latent space. So our method doesn't try and do that. We use the latent space to give our method, I guess, some information or some representation of each of the nodes, but we don't try and walk around in that latent space. The latent vector with each node is then used by our system to generate new molecules, and we can sample from that latent space, but we don't try any optimization within it.
Only one last question.
So maybe I missed, but I'm curious about what kind of algorithm to use, encoding or decoding in your, so graph to latent space or latent space to graph?
Graph to graph.
Yeah. Graph to graph?
Yeah.
I will ask you when the post the session more. Yeah.
Yeah, no, thank you.
Just go for the last question while we set up the next speaker. Your voice is not. Can you talk in the microphone, please?
I wonder how differential it's not working.
Okay. Okay, just shout.
So I wonder how differential compared to the constraint graph. Original encoder for molecular design for in the Generative 2018 conference. Is your method motivated from that paper?
Absolutely. So our generative procedure is very similar to that paper, and we took a lot of inspiration from that in order to design how we generated. We train in a very different manner, and when we generate, as I was mentioning, I guess one of the differences is we generate based on some pre-selected subgraphs which represent the fragments versus generating completely from scratch. So I guess inspiration in the design process, but a different formulation. But I think that's a really great framework, and I really like it. And
and could you comment if you actually switch to a cyclogram manner, because it's also for some kind of mapping from a data distribution to another data distribution. So it's kind of similar. So are you aware of a framework called cyclogram?
I think the answer to this might be quite long, so it's maybe better we chat later.
At the poster, okay?
Yeah.
Thank you very much.
Thanks.